Yeah, I have shown yesterday del dot E. Okay, if you take divergence of electric field at any position in space, the point operation, I told like that, am I right? We take derivative at some point, am I right? Like that. So we have to take, we can take derivative, we can take divergence of electric field at some point in space, then that will be equal to charge density at that point divided by epsilon. Is that okay? Now let me take one region, one volume. Okay, let me take one volume. Let me apply my, I'm going to do volume integral of this one. So over one complete volume. Okay. So now that's equal to integral of rho of r d2. Alright. Rho of r d2 divided by epsilon naught. I can take that epsilon naught outside. Isn't it? So now if you convert using Gauss divergence theorem, what is that one? Is equal to closed surface integral of, speak out, closed surface integral of E bar dot dA bar. So that's equal to 1 by epsilon naught. So volume, what is this volume? Volume within this surface, within this closed surface. So volume integral of rho of r d2. Volume integral of rho of r d2. Is that okay? Now what is this one? This is the net charge within that volume. Isn't it? There is a net charge within that surface. That's why we write Qn closed by the surface by epsilon naught. Isn't it? So, integral form of Gauss law. Okay, integral form of Gauss law. So now the next one is application of Gauss. Remember, once I write this one, I can take any volume anywhere, isn't it? This is true for all surface. Okay, so any shape of the surface, remember. But earlier I tried to prove using a kind of a spherical surface, am I right? So by taking one charge at the center. Now look at here, this is pure vector calculus. So this is true for any surface. Only thing you have to take care is, while doing volume integral, so you have to take the volume within that surface, or you have to take charge enclosed by the surface. Surface can be of any shape. Okay, so that's why he writes one sentence. Gauss law is always true, but it is not always helpful. Is that okay? It's always true for any shaped surface. Only for some symmetry, you can use that Gauss law to find electric field. Now let us solve that kind of problem. Okay, so application of Gauss law. Applications of Gauss law. There is Gauss's law, am I right? Now, first we shall see that Gauss law in an integral form. E bar dot dA bar. Now, I think you can do problem number 2.9, okay? Problem number 2.9. Ninth problem in the second chapter. Because now you have a tool from vector calculus also. Okay, do that. So now let me go for application of Gauss law. That's equal to Q enclosed by epsilon naught, or sometimes we write integral of rho d2 1 by epsilon naught rho d2. Sometimes that is written like that. When you see this one again, yeah, you can use this one to find electric field. But look at that one. How do you use this one to find electric field? It is inside the integral. Electric field, one thing you can observe is electric field is inside the integral, isn't it? And other one is, it's not again inside, not only inside the integral in terms of dot product, isn't it? So that's why you can just see this one like this, mod E, mod dA, cos theta, am I right? Look at here. So that's why Gauss law can give us only magnitude of the electric field. Is that okay? Since inside the electric field, it is in the dot product. Okay, we should know that direction of the electric field prior to use that Gauss law. First you have to find, first you have to judge by inspection. First you have to judge what is the direction of the electric field. Is that okay? And second one is you have to judge what is the dependency of electric field. Then only you can use that one, because it's not straightforward formula. Our Coulomb's law was very straightforward. It was integral, am I right? But here it is not straightforward. It is inside the integral. Because of the fact that it is inside the integral, first you have to judge two things. So 2 to 3 things. Let me just list out. One is which by inspection. Am I right? So you have to judge. First one is direction of electric field. First you have to judge direction of the electric field. Second one, dependency of electric field. I mean dependency of magnitude. I mean if you take Cartesian coordinate, whether it depends on x, y, z like that. Polar coordinate, r, phi, theta like that. Is that okay? You should quote the dependency. Okay. So now you can ask question. Yeah, if we find these two by inspection, okay, why we need Gauss law? No, it's not complete. Am I right? You are getting only dependency, only direction. You are not getting exact magnitude, exact dependency. Dependency means, wait a second, functionality. Better to say functionality. Better not to say dependency. Okay, you will not get dependency by inspection. Functionality. So, is there a word like that? Functionality. But write like this. I mean, we can only say by inspection whether it is depending on x, y, z, r, theta, phi, like that. Okay. We can't say it is inversely proportional to r, inversely proportional to r square like that. We can't say like that. So by inspection we have to judge these two. Then Gauss law will give exact magnitude. Are you getting my point? Because look at the theorem, Gauss law. So it is inside the integral, again in terms of dot product. Is that okay? Since it is in terms of dot product, to choose a surface properly, you should know what is the direction of electric field. Isn't it? Yeah, now we shall start that one. So there are 3 cases where we can apply Gauss law. One is spherical symmetry, other one is cylindrical symmetry, third one is planar symmetry. Okay. So again, we better to start with some problem, then I'll explain. Only 3 cases, 3 different symmetry problem that you can apply Gauss law. Now, find the field outside uniformly charged solid sphere of radius r. The question is that okay? Yeah. Gauss law, yeah, just continue. Then, Gauss law gives magnitude of the electric field. Gauss law means magnitude of the electric field. So Gauss law gives only magnitude of the electric field. Now let me start with the question. A uniformly charged solid sphere of total charge Q. Uniformly charged. Total charge Q. Total charge. It is uniformly spread throughout the volume. Okay. Of radius capital R. Of radius capital R. So total charge Q uniformly spread throughout it. Okay. So find the electric field. Find the electric field outside the sphere. Find the electric field outside the sphere. First thing you have to do is you have to first choose the origin. Okay, origin of your coordinate system. Let me choose origin somewhere here. Is that okay? At the center of this sphere, uniformly charged solid sphere. Okay. Now once I choose what you call center as the origin, so I can again, this is a kind of spherical symmetry problem. This is a kind of spherical symmetry problem. If I choose this one as the origin, now, so can I say this is the distance r from the origin? Okay, can I say distance r from the origin? My aim is to find electric field at this point due to this uniformly charged solid sphere. Earlier he has given this question, I told you to skip that one, isn't it? You can do it by your Coulomb's law, that integral, but that integral is too lengthy. Okay, now we have to apply what you call Gauss law. Now, what is the first thing that we have, what is the two things that we have to do by inspection? One is direction of electric field, second one is what you call dependency, I mean functionality. Is that okay? What is the direction of electric field now? No, yeah, radially outward. So now if you are in the spherical polar coordinate, you have to talk about r cap, theta cap, phi cap. Now electric field is along y. Again by inspection. Why? You said electric field, if it exists, it should be radially outward. How did you set like that? So can I take it like this? So let me take one vertically above point here. Okay. So now if you take small dq here, so there exists a similar small dq here. So both of these will produce electric field like this, and whose horizontal component cancel out, vertical component add up, isn't it? And again, so if you do the same thing in everywhere, you will get electric field outward, isn't it? So that's one argument. So what is other argument? There is no reason why it should be along theta cap or phi cap. That's not a good argument, but still sometimes we do like that, isn't it? Are you getting this idea? So take one, I mean, so vertically means you can feel that one, isn't it? You can, so for one elemental charge, there exists other elemental charge which cancel out horizontal component here, vertical component will add up. Again, you can take the points like this everywhere and you can say your electric field is along r cap, radially outward. Whatever the point you take. Again, because of symmetry only. He just state in one sentence, electric field is radially outward because of symmetry. But you should be able to argue if I ask, why it is radially outward. Is that okay? Okay, now electric field, can I write like this? By inspection, I got electric field mod E into r cap. It's radially outward, wherever you take. Wherever you take. Here if you take, it will be like that. Here if you take, it will be like this. Am I right? Electric field will be radially outward because of symmetry. Next one is functionality. Am I right? So what is the function of magnitude of the electric field? I mean, if you are in the spherical polar coordinate, you have to think about r, theta, phi. Is that a function of r? Is that a function of theta? Is that a function of phi? Is the question. Function of r alone. Why not theta and phi? Why not theta and phi? Speak out. Need argument. That's correct. Electric field is a function of r alone. Okay, electric field is a function of r alone. Why? Again, because of space symmetry. You don't have other words. Now look at here. Again, you should be able to argue. You should be able to convince. Remember. If you have a point here, suppose if you rotate this sphere, will you feel any change? Are you getting my point? It is uniformly charged solid sphere. There is no non-uniformity. If you rotate this one, will you feel any change? Or suppose if you take one spherical, if you take one sphere which centered at the same point, if you take one sphere which centered at the same point, which is concentric to this one. So if you move on that sphere, you will not feel any difference in the, what you call, magnitude, isn't it? Why? Why it would be different? Am I right? So at different point on this sphere, you will never feel any difference in the magnitude. Direction is different. Here it is like that. Here it is like that, isn't it? I mean, direction is different. But magnitude will not vary if you take a sphere which is passing through that point and centered at the same point, isn't it? So that means if you change theta or phi, magnitude of the electric field is not changing. If you are changing theta and phi by keeping r constant, you are not feeling any change of magnitude of the electric field, isn't it? So that's why it is independent of theta and phi. It depends only on r. When you change r, that means you are moving away from the charge distribution. Remember. Are you getting my point? You are moving away from the charge distribution. So that's why when you change r, radial distance, then obviously electric field magnitude should change. So its magnitude should not change. If you keep r constant, if you change theta or phi, its magnitude should not change. Or so keep your point in space same. So rotate that sphere, then also you will not feel anything different, isn't it? So what else you can argue? You have to argue that it should be function of r alone. It is independent of theta and phi. What else you think? Speak out. Wait a second, I was thinking about something. Why it is not depending on theta and phi? One thing is when you move, you will not feel any different. Okay. Yeah, that's the best idea. Okay, that's the best idea. When you move on a sphere, on a spherical surface with the same radial distance, you should not feel any different magnitude, isn't it? Again, because of symmetry only. So third one is again, we shall see Gauss law now. E bar dot dA bar is equal to Q enclosed by epsilon naught. Now we shall see Gauss law, isn't it? Now we have to make use of Gauss law to find magnitude. Am I right? Now I got only, it is a function of r, it is along r cap. I got only these two ideas by just inspection. So third one is I have to find the magnitude properly. So to find the magnitude, this magnitude should come out of the integral, isn't it? So again, so see that Gauss law, observe that Gauss law carefully. E dA cos theta. Am I right? Q enclosed by epsilon naught. Now look at here. So you have to choose the surface in such a way that this electric field should come out of the integral. You have to choose the surface to, in the application of Gauss law, while applying Gauss law, you have to choose the surface in such a way that electric field magnitude is constant throughout the surface. One thing. Other one is this cos theta should not take different value at different point. Is that okay? Then how do you choose the surface? Spherical surface, that you already know, isn't it? Now look at here, once you, again, so, but see that one, see the necessity here. See the necessity of choosing spherical surface. We call that one as Gaussian surface. Am I right? So now, while applying Gauss law, one thing is you need electric field at this point. Am I right? Your surface should pass through this point. Are you getting my point? So, you are going to find the electric field at this point, your surface should pass through that point. Then only you will get magnitude of the electric field at that point. Isn't it? Because Gauss law is the surface integral. This part is a surface integral. So, second one is, so again, throughout the surface, your electric field should be constant. Then only you can take electric field outside the integral. Not only electric field, this cos theta should also give the only one value. Is that okay? So, this E cos theta, that should be same. So, that's why what we are going to do here is, we are going to take a spherical surface. We call again imaginary surface, okay? Imaginary surface. So, on which we are going to apply Gauss law. Okay, spherical surface with radius small r. Okay, why I have taken like that? Because I need electric field at this point. My surface should pass through that point, remember. Is that okay? So then I am going to take this one as my closed surface and I am going to apply my Gauss law. E bar dot dA bar is equal to Q enclosed by epsilon naught. Now look at here. So if you take this closed surface, look at here, at any point your area vector is radially outward, isn't it? At any point, your electric field, what is the electric field direction? So do it in pure coordinate geometry. This is the best idea. Is that okay? So now let me generalize the whole statement. Okay. So now look at here. Once you apply your Gauss law to this closed surface, at each and every point on the surface, your area vector is also radially outward, and your electric field is also in the r cap direction, isn't it? So that's why you can write in the next step mod E into r cap. Am I right? Magnitude of the electric field at a distance r into r cap. R cap is the direction. Dot product with dAr is equal to Q enclosed by epsilon naught. We shall think about this one later. Now, what is that area vector which is along r cap direction? Are you getting my point? Why area vector is along r cap direction? Because it should be perpendicular to the surface, outward from the region. Outward from the region of that surface, remember. Okay. So, what is that one? H theta, H phi, d theta, d phi. What is H theta, H phi? R square sin theta, d theta, d phi. Look at here, r is constant. Throughout the surface, r is constant. Obviously, theta and phi are variable. Is that okay? Your Gauss law becomes r cap dot r square sin theta, d theta, d phi, r cap. Okay. So that's equal to Q enclosed. What is the net charge enclosed? Total charge enclosed. You can do volume integral of charge density also, but that's not needed. You know what is the total charge inside, isn't it? What is that one? Q, small q. Isn't it? This, we call this one as Gaussian surface. This Gaussian surface encloses entire charge. Am I right? Total charge enclosed is that one. Okay. Even if you take a rho, volume charge density, if you want to integrate, you have to integrate from 0 to r. Then also you will get the same thing. So better not to make it complex. Again, there are problems like that. Okay. R cap dot r cap 1. Am I right? Now look at here. Throughout this surface, magnitude of the electric field is constant, because this is the surface with constant radial distance, and electric field depends only on the radial distance. So that's why, can I take electric field outside? Mod of E closed integral of r square sin theta, d theta, d phi. Look at here, r square will also come out. Why? Throughout the surface, the r is constant. Remember, this radial distance is constant. Is that okay? So this is the sphere which contains charge. Okay, is equal to, again, Q by epsilon naught. To integrate throughout the surface, sin theta, d theta, d phi is a kind of solid angle. Am I right? This was solid angle. We have discussed that here. It was 4 phi. Okay. So your theta should run from 0 to pi. Pi should run from 0 to 2 pi. That's it. You will get 4 pi. Am I right? So what's your answer? Again, you have to write this step very quickly later. Okay. So first, try to get each and every idea. 4 phi. Am I right? Is equal to Q by epsilon naught. Magnitude of the electric field 1 by 4 phi epsilon naught Q by r square. By inspection, we already got what is the direction. Now, how do you write? Electric field vector 1 by 4 phi epsilon naught Q by r square. We already know it is along r. Outside, okay? Outside. Electric field outside the uniformly charged solid sphere. Better write out. Inside it will be different. We shall show that one. Yeah, reply with yes. Over. Now observe one main point here. You have to choose your Gaussian surface so that over the Gaussian surface, electric field should be uniform, and over that Gaussian surface, electric field and area vector should be along the same direction. Then only this electric field will safely come out of the integral. Is that okay? Can you write that sentence? Generalization. You have to choose the Gaussian surface in such a way that mod of electric field should be same over the surface. Mod of electric field should be same over the surface. And electric field and dA vector should have the same direction over the surface. Mod of electric field should be same over the Gaussian surface, and electric field and your dA vector should be same over the Gaussian surface. So then only, write down, then only electric field will come out of the integral, surface integral. Write down like that. Then only electric field will come out of the surface integral. Then only electric field will come out of the surface integral. Now look at here. So that's the generalization. Okay, whatever the situation you take. Look at the last answer, electric field outside. It looks like it is due to point charge, am I right? Electric field due to this, this is equivalent to for outside point, this is equivalent to, if you place Q charge here, if you are talking about electric field at this point at a distance r from here, both are equivalent. Are you getting my point? So that means, can you write one sentence? The field outside a sphere, uniformly charged solid sphere, okay? The field outside uniformly charged solid sphere, write like that. The field outside uniformly charged solid sphere is exactly the same as it would have been if all the charge had been concentrated at the center. We can learn a lot of grammar in this sentence. Is that okay? So because when you see last formula, it looks like that, am I right? It doesn't matter whether you have a distribution or a point charge at this point. So your last answer would be same, isn't it? Again, only for outside, okay? Inside that would be different. So now, again, we can use Gauss law in similar manner, only three different cases. One is, this is spherical symmetry. Other one is planar symmetry. So other one is cylindrical symmetry. Is that okay? Now we have to take one more problem on cylindrical symmetry. Okay? Wait a second, let me do one more problem on spherical symmetry, then we shall go for cylindrical symmetry outside this one. Find the electric field. So 2.14, problem number 2.14. Okay, 2.14. Rho is equal to K into R. I mean, you have a solid sphere of radius capital R, but it is not uniformly charged. It is not uniformly charged. Find the electric field inside the sphere that carries a charge density that is proportional to distance from the origin. Suppose if you take the origin here, so charge density is equal to K into R. Okay. Outside this sphere there is no charge, but within that sphere charge density varies like that. Are you getting my point? Now you have to find electric field inside that one. You have to find electric field inside that one. Let me do this one. Is that okay? So as a homework, you do electric field inside uniformly charged solid sphere of total charge Q. I have done for outside, am I right? You do inside of uniformly charged. This is non-uniform charge. Is that okay? So uniformly charged means you can write rho is equal to total charge by total volume, 4 by 3 pi r cube. That's constant throughout that region. But here rho is not like that. Rho equal to K into R. Is that okay? It depends on R. At exactly middle, I think charge density would be 0 because R equal to 0. So when you go to the edges, charge density is increasing like that. Okay. Now I need to apply again Gauss law to find electric field inside this one. Okay. Electric field inside this one. Now look at here. So to find electric field at any point inside, you have to again take Gaussian surface which passes through that one. Now all of the argument remains the same. What are the argument? Electric field should be radially outward. Magnitude of the electric field should be depends on only on R. Those arguments remain the same for spherical symmetry problem. Is that okay? Electric field should be along R cap, and magnitude of the electric field should depends only on R. Is that okay? There should be no reason why it should depends on theta and phi, because when you rotate the system, so nothing is changing, isn't it? So one more thing, so there is no reason why it should be other than R cap, isn't it? Or if you take any point here, so again because of symmetry, again you will get radially outward electric field only. Is that okay? You can just cut down the whole structure into two parts, am I right? You can see that, isn't it? You can cut down whole structure into two parts. At this point, you can see the whole structure. Look at here. So electric field due to all charges left hand side and so right hand side and left hand side, they will give net resultant radially outward only, whatever the point you take. Okay. Again, you have to take these 2 points. One is electric field depends only on radial distance, and electric field direction is always radially outward. And obviously, you have to take your Gaussian surface like this. Don't take Gaussian surface outside. We need electric field inside. Our Gaussian surface should pass through that one, because our electric field is inside the surface integral, isn't it? So now this is my Gaussian surface. Now I am going to apply Gauss law. Is that okay? Now again, all arguments are same. Your dA vector, it is radially outward, it is along R cap, and your electric field is also radially outward, isn't it? Over that Gaussian surface, your electric field and your area vector are along the same direction. So again, magnitude of the electric field depends only on R. Is that okay? So let me take, this is the Gaussian surface of radius R. Is that okay? Because you need an electric field at a distance R from the origin inside the sphere. Is that okay? At a distance R from the origin inside the sphere. Okay. So now once you apply Gauss law, what is electric field? Mod of E into R cap. What is this DAR? R square sin theta d theta d phi R cap. That's equal to, now while finding enclosed charge, remember Gauss law, in Gauss law, only charge within that spherical surface comes. Charge outside the spherical surface will not come. Why? Any idea? This is the net flux, am I right? This is the net flux. This part is net flux through the closed surface. Why only in the right hand side, only charge within that surface comes? Why not outside? Outside charges will generate electric field. It will pass through the surface from one side. It will go out from other side. Remember. Is that okay? So that's why charges outside will never contribute to the net flux of any closed surface. Any closed surface you take, charges outside the closed surface will never contribute to net flux to any closed surface. Is that okay? That's why only you have to concentrate on net charge inside. We shall find that one. Okay, we shall find that one. So let me, for a time sake, let me write Q enclosed by epsilon naught. Now look at here, this part remains the same. Now electric field is constant throughout the surface. You can take it outside. Mod of electric field. Again R is also constant radial distance over the Gaussian surface. R square come out. So sin theta, d theta, d phi. So to integrate throughout the surface, your theta should run from 0 to phi, phi should run from 0 to 2 pi, isn't it? Q enclosed by epsilon naught. Look at here, mod of E R square into 4 phi is equal to Q enclosed by epsilon naught. This part will be same for all spherical symmetry problems. You can again practice, you'll get that idea. This part will be same for all spherical symmetry problems. Whether you take inside, outside, this part will be same. Only this part you have to take care of. Now what is the charge enclosed? Now you have to integrate to find Q enclosed. Why? Because your charge density depending on the radial distance. What is that volume? What is that volume? Volume within the Gaussian sphere. What is that volume? Volume within the Gaussian sphere, isn't it? Q enclosed. What do you mean by enclosed? Enclosed by this surface. This is the Gaussian surface, isn't it? Now, how do you do that one? How do you do that one? So, do it again. So, rho, this scalar, whatever rho, it is written in terms of, again, it is in terms of R. Don't do that one in Cartesian coordinate again. Okay, you have to go for spherical polar coordinate. Rho equal to K into R. What is D2 in spherical polar coordinate? R square sin theta dr d theta d phi. Your R should run from 0 to small r. Isn't it? You have to, how do you do that volume integral? Or how do you find the volume of that sphere? Your R should run from 0 to R, theta should run from 0 to phi, phi should run from 0 to 2 phi. That will become complete volume integral of the sphere, isn't it? So theta should run from 0 to phi, phi should run from 0 to 2 pi. Over? So now look at here, sin theta d theta d phi. Can I take that integral one side? Because that is 4 phi, isn't it? So what is R K outside? What is R integral? R cube dr 0 to R. R is also variable, volume integral. Okay, this region, I am talking about this region. What is this one? K R is to 4 by 4 running from 0 to R, 4 phi. Am I right? Now can I equate left hand side and right hand side? Mod of E R square into 4 phi, that's equal to Q enclosed, that is K R raised to 4 by 4, am I right? Upper limit minus lower limit into 4 phi divided by epsilon naught. This is Q enclosed. 4 phi got cancelled. electric field magnitude, that's equal to, any idea? K r square by 4 epsilon naught. So it is electric field vector I better write inside, electric field inside the sphere. Now look at here, functionality, it's proportional to r square now. Now can you find electric field outside this one? While finding electric field outside, your Gaussian surface should be outside. Then while finding net charge enclosed, how do you take r integral? 0 to capital R, because outside the sphere charge doesn't exist. Be careful, okay? Do that one. Let me again explain a couple of problems. So now your mind have to think about that one. Where is the charge? Again, ultimately this is the most general formula. Am I right? E bar dot dA bar surface. Okay. So that's equal to 1 by epsilon naught integral rho d2. Am I right? Charge enclosed. What is this volume? Volume within this surface. Now you should know what are the location of the charge. You should know where is the charge. So where is no charge. You should know them. Okay. While doing this volume integral, be careful. Outside. So again, while doing outside, you are going to run your Gaussian surface so bigger than this radius. Am I right? But your charge extends only within this region. While doing this volume integral, run your radial vector, so radial distance from 0 to r, because outside that one, charge just doesn't exist. Okay. So try to think geometrically. Okay. A whole thing can be imagined. Okay. Spherical symmetry problem. Yeah, there will be charges here. Yeah, but look at here, our again, ultimately everything is from your superposition principle also. Okay, you can find electric field due to outside charge. You can find electric field due to R. You can find net flux due to outside charge. You can find net flux due to inside charges. Net flux due to outside charge is always 0 for any closed surface. You are saying while finding electric field, you have to take outside charge also, am I right? But whatever, it will never be along r cap or phi cap. It will be always along, it will never be along phi cap or theta cap. So even if you take electric field outside, remember, you will get electric field along r cap only. That will not change. No, it will not affect the direction of the electric field. It will not affect functionality of the electric field. Electric field will never depend on theta or phi. Electric field will never be along theta cap or phi cap. Yeah, definitely they will contribute. Yeah, definitely they will contribute. If you are going to do those integration of rho d2 r cap by r square, then you have to take entire charge inside, outside, everywhere. But our Gauss law will take care about only charges inside. Is that okay? So it's a kind of trick here, mathematical trick. Field outside? Wait. I didn't get it. Yeah. And I have taken total charge, Q. Yeah, definitely. Yeah, there exist charges, Gauss law, but in Gauss law it will not come into play. Gauss law says Q enclosed. What is this volume? This is the volume within this surface, am I right? So that's why this only, this Q enclosed is only within that surface, not outside the surface. But if you are talking about your Coulomb's law, you have to take care. But if you are talking about Gauss law, this is a net flux. It depends only on the charges inside. That's what I'm saying. You are applying Gauss law. Again, you are thinking about Coulomb's law, isn't it? Outside charges will also contribute to the electric field. Yeah, they will. If you use Coulomb's law, they will. you have to take care about entire charges. But in Gauss law, they will not come into play because this part is net flux. Are you getting my point? That's how this becomes one mathematical technique. Is that okay? If you are talking about Coulomb's law, definitely you have to take each and every charge and you have to vectorially add them. So that's how we do electric field at a r, that's equal to 1 by 4 pi epsilon naught integral of rho of r prime d2 prime by r square r cap. Am I right? Look at here. That's the kind of vector integration, isn't it? Yeah. Yeah, this is a Coulomb's law. I'll call this one as a Coulomb's law, isn't it? I mean, a kind of Coulomb's law. So now, if you want to use that one, it's a kind of vector addition, but in an integral format. You have to take entire distribution. You have to take contribution by the entire charge distribution. But Gauss law, this part is the flux, total flux through the closed surface. Then, so that depends only on the charge enclosed by that one. Outside charge will not contribute to the flux. You can think like that. So, or if you are thinking about Gauss divergence theorem, you have related them. Do you remember earlier? So, my derivation. So, that's why, what is this volume? This is the volume within this surface. Is that okay? That's why that should be charge enclosed within that surface. So, charges outside the surface will not come into play. Okay? Yeah, this is non-uniform. That's why you need to do this one. So, in the earlier case, we know already net charge is Q. That's why we just substituted. Suppose in this problem, if you want to find electric field outside, now you have to, he hasn't given what is the total charge. He has given only rho. He hasn't given total charge is Q. So, that's why you have to integrate that one. So, this one, you have to take this region and you have to find the total charge. Okay. So, do problem step by step, okay. So, he has given the problem in, I think, problem number 2.9. He has given charge density. He asked you to find charge within some region or like that. In that problem, you have to integrate and you have to find the charge. Do problem number 2.9, ninth problem. So, then again go for this Gauss law problem, okay. In that problem, we will get the imagination, how to find charge within some region. Okay. Now, but be careful, outside this sphere, there is no charge. Inside the sphere, your charge density varies like K into R. Okay. Now, quickly let me go for cylindrical symmetry problem. Okay. Do all spherical symmetry and cylindrical symmetry problem today, before evening, okay. We shall invest some more time on this one. Cylindrical symmetry problem. Example number 2.4. Example number 2.4. A long cylinder, remember, long, it should be long, it should be infinite, mathematically. A long cylinder let me tell you why it should be long, otherwise it will not become cylindrical symmetry. Is that okay? If it is not very long or if it is not infinitely long, it will not become cylindrical symmetry. A long cylinder carries a charge density that is proportional to distance from the axis. Charge density is not uniform here. Okay, charge density is not uniform. So, charge density is equal to K into S. Suppose if you take n, suppose this is my Z cap. You can take this is my Z cap of your cylindrical coordinate. Is that okay? So, distance, perpendicular distance from the Z cap is your S. Am I right? Are you getting my point? Suppose this is Z cap. This is S. So, perpendicular distance from the Z cap is S. So, at any point, charge density is proportional to distance from the axis. Therefore, rho equal to K into S. For some constant K. Find the electric field inside the cylinder. And the electric field inside the cylinder. This is infinitely long, remember. This is infinitely long. Find the electric field somewhere at a distance S inside that. Is that okay? So, what is the first thing that you have to do? You have to first argue what is the direction of the electric field, what is the dependency, what is the functionality, isn't it? unless you can't imagine Gaussian surface. Is that okay? So now rho equal to k into s, I need electric field at some point s from the axis. I have to, if you talk about cylindrical coordinate, you have to talk about cylindrical variable. Now I have to find electric field at a distance s from the axis. Can I say like that? Now, rho equal to k into s. I need electric field here. Now, what is the direction of electric field at a point s from the axis? Any idea? Direction. I'm talking about a direction. Don't say r cap. You have to talk about s cap, phi cap, or z cap. You are in the cylindrical coordinate now. Why? No, don't say like that. Try to argue. So, suppose if you have taken point here, suppose take two elemental charge here, it will produce electric field in this direction. Isn't it? So again, there are as many charge, the charge distribution is same right hand side and left hand side of this line, am I right? That's why they should contribute this kind of electric field. You have to imagine like that. Whatever the point you take, you can argue like that. That's why first thing is, at any point, electric field direction should be s cap according to our cylindrical coordinate. Or you can say axially outward. You better say like that. Axially outward. This is the axis. It is axially outward. Okay. Next one, dependency. Magnitude of the electric field depends only on so does it depend on phi or z? Why? Z is infinitely long. Why it will not depend on z? You may say it will not depend on phi, because when you move in a on a line with a, so by keeping s and z constant, you will not feel any difference. Am I right? If you move along a circle with centered at this axis, isn't it? You will not feel any difference. There is no reason why it should depend on phi. Again, why it will not depend on z? That's my question. So because when you move along z axis, look at here, it is infinitely long here as well as here. Okay, infinity means when you move along, when you just walk along z axis, you will feel it is infinity in this side, in this side. You are not seeing that end. Are you getting my point? You may give that one as long. Mathematically, we have to take infinitely long. Is that okay? So now look at here. When you move along z axis, you will feel that it is infinite in the forward as well as backward, isn't it? Suppose you are standing here. Okay. So, and I'm going to tie one towel to your eyes. Is that okay? So then I'm going to displace you to this point. Now you will not feel any difference. Why? When you, so again, how do you say your position? By just comparing your environment, am I right? When you see here, you are seeing this side infinite, and you are at a distance s from the axis. So when I displace from this point to this point, again, how do you see this one? Again, this side infinite, you are at a distance s. You will not feel any difference. Or when you move along z axis, magnitude of the electric field will not change. That means it should be independent of z coordinate. Is that okay? Again, it will be independent of phi. That's why only dependency is, if it depends, it should depend on s. Is that okay? Yeah. Again, why electric field cannot be z cap direction? Because of that fact, again, you have to take some elemental charge so that they will add up to give electric field like this, whatever the position you take. Okay, whatever the position you take. Suppose you have taken electric field somewhere here. So take a symmetry here. Look at here. So all of these charges will contribute to the electric field. It will be along either s cap or minus s cap. Usually s cap. Okay, it will never be along z cap. Okay, try to argue that one. Why it is like that? In your way, try to argue that one. So, and functionality is only s. Plane. Which plane? I'm not getting it. This one. There is no end. It is infinitely long. So that's why this cannot be applied for a finite cylinder. Are you getting my point? Finite cylinder will not have cylindrical symmetry. That's correct. Is it okay? If it were finite cylinder, suppose. So actually, I should have extended this one. Okay. Don't imagine this one like a finite cylinder. That's correct. Okay. If it were finite cylinder, then you are correct. Suppose if you take any point here or any point here, then electric field will be somewhere here, isn't it? Some electric field, horizontal, vertical component, you will get electric field somewhere here. Finite cylinder, it's not cylindrical symmetry. Okay, that's correct. You are talking about edge, am I right? Now, there is no edge here, it is infinitely long. Then that question will not arise. Is that okay? Again, ultimately, our practical situation is very long cylinder. Mathematically, we take infinite cylinder. Practically, we can apply the formula, whatever we derive here, for a long cylinder. That's why he gives the question as long cylinder. Okay, mathematically, you have to imagine it's an infinite cylinder. There is no edge. If suppose it is finite, as you said, electric field may have z cap component. Definitely, it will have z cap component. Okay, since it is infinitely long, whatever the point you take, now look at it, let me argue like that. Suppose I'll take this point. Now also this side you have infinitely many charge distribution. So this side you have infinitely many charge distribution. They will contribute like this. Let me argue like this. Isn't it? Wherever you take, you will get electric field along S cap only. Okay? So first try to argue that by assuming it is of infinitely long. Okay? So next one is how to run your Gaussian surface. Yeah. How to run your Gaussian surface? First thing is Gaussian surface should pass through your point of interest. So then, it's a kind of cylindrical surface. Which pass through our point of interest. Is that okay? With the axis of the cylindrical surface same as the axis of our charge distribution. Okay. Now look at here. This is my Gaussian surface. Closed surface. It should be closed surface. Remember. Okay. Now I have to apply Gauss law to this surface. Closed surface integral of E bar dot dA bar is equal to Q enclosed by epsilon. So full problem in cylindrical coordinate. Okay. Now this Gaussian surface, now it contains your what you call curved surface as well as two end surface, planar surface, isn't it? Along that curved surface, you will get electric field. Look at here, if you take any patch of area here, what is your area vector? It is along S cap, remember, isn't it? If you take any point, what is your electric field? Electric field is also along S cap. Throughout that curved surface, you are getting electric field and your area vector both are along the same direction. Is that okay? And throughout that curved surface, you are at the same distance from the axis, and electric field depends only on the distance from the axis. That's why throughout that curved surface, your electric field is what you call magnitude of the electric field is same throughout that curved surface. So now what about this end surface? Surface integral of end surface. For that end surface, you have to take dA vector like this, or dA vector along z cap, or minus z cap. But your electric field is along S cap. S cap dot z cap 0. Or there will be no flux. Again, this is a total flux. Am I right? You are finding the electric flux. There will be no flux. So through this end surface. Why? Electric field is like this. Your area vector will be like this, perpendicular. So that's why. So I can just write this one as curved surface E bar dot dA bar plus planar surface end surface, planar surface. So E bar dot dA bar, that's equal to Q enclosed by epsilon naught. Is that okay? Q enclosed by epsilon naught. Is that okay? So now look at here, this is 0. Why? There will be no flux through that planar surface because electric field is perpendicular to surface area. This is 0. You have to do only this one. Again, while doing that curved surface integral, your electric field is, again, you can apply all of your coordinate geometry here. Curved surface integral, mod of E into S cap. What is dA vector? So throughout this curved surface integral, wherever you take, dA vector is along S cap direction. Isn't it? So dA vector is along S cap direction. What is that one? H phi, Hz, d phi. H phi, Hz, d phi, dz. dA vector, H phi, Hz along S cap. d phi, dz, S cap. What is H phi? Yes. Yes, d phi, dz. Check it out. Yes, d phi, dz. Now I haven't said what is the length of this one. I have to find the, I should have dimension. Radius of this cylindrical surface is yes, obviously, because you needed electric field at a distance, yes. What is the length? Length, take it as L. Length of that Gaussian surface. This is a Gaussian, this is an imaginary surface. Okay? Are you getting my point? This is an imaginary surface on which we are applying Gauss law to find electric field. Okay? Length of that the cylindrical surface is L. Take it like this because you have dz as a variable. Am I right? You have to integrate with respect to dz. Now you can choose your origin somewhere here, and this is your z cap. So that when you integrate along z cap, you will get length L. Okay, we shall see that. Now your curved surface integral mod of E S cap dot product with S d phi dz S cap is equal to Q enclosed by epsilon naught. We shall take it later. Okay, we shall take it later. S cap dot S cap. Again, electric field is constant throughout the surface, curved surface. Integral S is also constant throughout the curved surface. Okay. So write it yourself. Don't look at the board. D phi dz. Again, it's a double integral. We prefer writing only one integral symbol. Whenever you need, you take the double integral. Okay. Now, how does d phi run from? So, throughout this curved surface, phi should run from 0 to 2 phi. Okay, 0 to 2 phi. How does your z run from? So, you can choose origin here. Your z runs from 0 to L. This is a L. This distance is L here. Is that okay? So, that's why mod of E, yes. What is this one? So, 2 pi into dz, integral of dz, L. This is pure coordinate geometry way, okay? But that is very safer. That's very safer. It's hard to learn that one. So now, how do you find charge enclosed? Again, you have to go for rho d2, am I right? And you have to integrate throughout this volume inside the Gaussian surface. Don't take outside region, okay? So now, what is that rho? K into S. What is d2 in cylindrical coordinate? S ds d phi dz. Check it out. Now you have to integrate, isn't it? Now what is your S run from? 0 to S. Phi run from 0 to 2 phi. Z runs from 0 to L. So do that Q enclosed also. Do this integral. K 0 to S, S square ds, 0 to 2 phi d phi, 0 to L dz. Can I write like this? Z is from 0 to L. Or you can choose origin anywhere, okay? Anyway, if you do this integral, you will get length L. Integral of dz throughout this one, you will get length L, okay? You can choose origin anywhere. So this will be K Q enclosed. S cube by 3, am I right? S cube by 3, what is this one? 2 pi into L. Now look at here, Q enclosed. So K S cube by 3, 2 pi into L, this got cancelled. Okay? Electric field is equal to K S square by 3 epsilon naught. I left epsilon naught. So at the end, electric field at a distance S inside the cylindrical long cylinder, K S square by 3 epsilon naught. You already know what is the direction. That's the answer. Over. Now let me just give one more idea. Last one. Do it quickly. While doing this part, usually electric field will come out, am I right? What you get? Integral of R. Usually we run our Gaussian surface in such a way that, so mod E, mod dA into cos 0 happens. Electric field when dA vector are along the same direction, and this electric field will come out, am I right? So when electric field comes out, that becomes integral of dA. What is this one? Integral of dA, mod of dA, that is surface area. Now look at here, whatever 2 phi L into S you have written along with electric field, what is that one? Curved surface area. You can write directly, isn't it? So you can write electric field into surface area on which you are doing the integration. You can directly write. Because our idea was that electric field should come out and area will left out, and direction between electric field and area vector should be same. Okay? You can write like this also, always. You can quickly write the step. But coordinate geometry is the most general way. Okay? Do in both ways. Do in both ways. Yeah, now you can solve all problems related to cylindrical symmetry and spherical symmetry. Problem number 2.11 to 2.16. 2.11 to 2.16 outside the chapter, outside this Gauss law. Spherical symmetry and cylindrical symmetry problems. Yeah. It is infinite length. Yeah. Now look at here. Yeah, it will never depend on length. Look at here, length got cancelled. It will never depend on Gaussian surface length. That's correct. Look at here, it is cancelled. If you take a larger Gaussian surface, charge enclosed will also be large. This area will also be large, so that they got cancelled. It will be independent of that. You can see that. Length of the Gaussian surface doesn't matter. Okay? I thought you were talking about length of holes. Length of the Gaussian surface, it doesn't matter. It got cancelled here. Yeah.
So if it's a point charge, it will produce electric field in all directions. There's a charge on the plane surface, Gaussian surface. And
wait a second. If you have a point charge, one thing is you better not to go for Gauss law. Coulomb's law is only one direct way of writing the electric field. Yeah. Then even if you want to go for Gauss law, take one spherical surface and apply that.
point charge will produce electric field in all directions.
All the r cap direction. That's what you are saying. All direction. Yeah.
There is two sides to the cylinder. There are the charges. It can produce electric field in outward.
Wait a second. You are mixing this problem along with this one. I mean, in the cylinder problem, am I right? You are placing charge anywhere.
There is a charge.
Where?
Because it is uniformly charge distributed
Okay.
at this
There are charges here.
and this to adjacent.
No, that is infinitely long. Don't go for it. You can't go for it. Okay, Gaussian surface. Yeah, that's correct. You said Gaussian surface, you have charges here, then Y flux is 0. No, that in one of the earlier problem we have seen, we had a charge Q here. Charge Q will produce electric field on the plane, and your area vector will be always perpendicular to the plane. Flux is 0. Is that okay? So that's why, again, here we argued in a different way. Electric field is along S cap. Here your area vector is perpendicular to S cap. That's why flux is 0. Even though if you argue there exist charges on that plane, so it will not produce any flux in the same plane. Okay? Yeah. Any question?